Up to this point, each chapter has built on earlier ones so that we have most recently examined the equilibrium of assemblies of rigid bodies. The last 4 chapters in this class fill in some of the details we've glossed over in our examination of equilibrium. In filling in these details, we also pave the way for the next set of topics in dynamics and/or mechanics of materials. Let's take a few minutes to discuss the relevance of these last 4 chapters before looking at the details of the content in Chapter 7. In Chapter 7, we are interested in finding the effective centers of distributed quantities. Mass is inherently distributed, and the mass of an object is the integral of its mass density over its volume. If we had to actually identify every increment of mass or weight in an engineering calculation, such calculations would be incredibly tedious. Instead, in many instances, we can replace a distributed weight with the total weight acting at an effective center. If the object is symmetric about one or more planes, it is intuitive that the effective center is coincident with a geometric center. But how do we identify such centers more generally? We will discuss the process by which we evaluate such centers in Chapter 7. The identification of a so-called center of gravity is crucial when we make the transition to rigid body dynamics. In Chapter 8, we again look at equilibrium of bodies, but now focus inside an individual body. We will be interested in finding internal force and moment distributions within beams. The combination of internal moment distributions with the geometric and material stiffness of the beam will allow us to define the deflections of such beams under load when we transition to flexible members in mechanics of materials. In Chapter 9, we consider one model of friction. This is important for many classes of problems, including those where pulleys are transmitting torque from one location to another. Finally, in Chapter 10, we consider rotational inertia. There are 2 kinds of rotational inertia important to us. The first has to do with the geometric stiffness of a cross-section and is called the area moment of inertia. The second has to do with the resistance a body offers to acquisition of rotational motion and is called the mass moment of inertia. The area moment of inertia is an important component of the bending of beams under load and is important in mechanics of materials. The mass moment of inertia must be found to understand how long it takes a body to spin up under torque, and so is important in rotational dynamics of rigid bodies. In these last 4 chapters, we also make a mathematical transition. Up to this point, we've needed geometry, trigonometry, and algebra to tackle problems. But distributed quantities represent continuously varying quantities, and calculus is the mathematics of continua. We will need to be able to evaluate integrals for some of our problems. In Chapter 7, we will examine centers of distributed quantities. Initially, in Section 7.1, we will consider centers of shape, also called centroids, and then in Section 7.2 consider centers of mass and gravity. In Section 7.3, we briefly take a look at a method useful for objects of revolution. Finally, in Section 7.4, we discuss distributed forces. One important application of such distributed forces involves hydrostatic loads. Throughout this chapter, we will discuss these various centers. We use these different terms to talk about centers of different kinds of distributions. For a large fraction of our problems, though, there will be no distinction between a center of shape, a center of mass, and a center of gravity. It will turn out that if the object in question is homogeneous, that is, it has a uniform mass density, there will be no distinction between center of shape and center of mass. If the object is in a uniform gravitational field, and this will apply to every terrestrial object, then there is no distinction between the center of mass and the center of gravity. So every object made of a single, uniform density material on the surface of the Earth will have identical centers of shape, mass, and gravity. We'll be able to see this shortly in a following section. As a way of introducing this material, Consider the case of a waiter transporting a tray of wine and pasta to your table after an arduous day of solving statics problems. You are really hungry, and you don't want the waiter to lose control of the tray as he brings it to your table. This requires the center of gravity of the tray and its contents to be positioned somewhere near the center of his hand so that his fingers and palm support the contents and they don't shift and fall off the tray. How do we determine the center of gravity for this problem? This is an application of equivalent force systems from Chapter 4. Recall how we found the simplest possible force system for a coplanar or parallel force system. First, we picked a reference point and found the resultant force and resultant moment about that point. And then two, we shifted the resultant force to a new position so that the resultant force exerted the same moment about the reference point that we calculated in the first step. Applying these two steps to this problem will enable us to find our center of gravity. In the present illustration, we will define the leading edge of the tray as the origin of our coordinate system and define distances to the wine, pasta, and tray from that origin. The resultant force is just the sum of the weight of the three objects. The sum of the moments of these three forces about point A would be 844 Newton centimeters. For the somewhat unusual coordinate system sketched in the figure, note that the right-hand rule requires Z to point into the screen so that in this particular illustration, clockwise moments exerted by these weights would be positive. The quantity x bar is the shift of the resultant force from A required to produce the same moment. It is 844 Newton centimeters divided by 30 newtons and equal to 28.1 centimeters. This shift, then, is the center of gravity of the system. For a more general number of objects, we'll call it n, the center of gravity is represented as the boxed expression at lower right. It is calculated as an average of the locations of all the objects, with each location weighted by its physical weight. As the phrase weight weighted is unfortunate, we could instead say that the center of gravity is a force-weighted average of all its constituents. Note also that since the weight is mass times the gravitational constant, there is no difference between center of gravity and center of mass in any terrestrial application. In all of our applications, we will use center of mass and center of gravity interchangeably, even though the former is a mass-weighted average of position and the latter is a force-weighted average of position. To see the importance of center of gravity or center of mass, consider the following. Newton's second law applies to particles. What happens when we consider a body? Here we have modeled a body as an assembly of n particles. If you like, you can think of a body as an assembly of atoms, so n would be very large. In writing Newton's second law for an individual atom, you'll notice an uppercase F meant to indicate an external force and a lowercase Fij meant to indicate the internal force between the atom and one of its j nearest neighbors. When we sum over all the particles or atoms making up the assembly, all of those internal forces cancel out. Since by Newton's third law of equal and opposite action and reaction, the internal force acting on particle I by nearest neighbor j is canceled out by the internal force acting on particle j by nearest neighbor I. When we have summed over all the particles in the body, the result is the sum of all the external forces acting on the body is equal to the sum of all the products of the masses and the accelerations of the individual particles or atoms. The total mass of the body is the sum of all of those particle or atomic masses, so we can write sum of all the external forces on the body is equal to mass times this quantity. The term in parentheses is the acceleration of the center of gravity, which is the second derivative with respect to time of the position of center of gravity. The components of that position vector are the x, y, and z components that we're going to be calculating shortly. So for instance, this will be equal to the mass weighted average of the positions of the individual x-coordinate values. This shows that the equation governing translational dynamics of a body looks exactly like that for a particle, as long as the acceleration on the right-hand side is that for the center of gravity. There is a complementary equation that can be derived to describe the rotational dynamics, but it is a more involved derivation, and I'll leave that to your dynamics class. The result is that the sum of the moments of the external forces acting through the center of gravity is equal to a mass moment of inertia, which we're going to talk about calculating in Chapter 10, times an angular acceleration. Although we can choose any point we'd like to impose moment equilibrium in statics, it turns out that there are a couple of special points in dynamics where rotational dynamics are most easily described. One of those is the center of gravity. Thus we see that rigid body dynamics in both translation and rotation necessitate identification of the body's center of gravity. In addition to center of mass or center of gravity, we can also define a center of shape. We refer to these centers as centroids, and we can define them for lines, areas, or volumes, depending on the application at hand. One of the things we cannot do with centroids is mix different types of shapes. We can define a center of area or a center of volume, but we can't calculate a center of mixed objects, areas and volumes together, for instance. Note also that all of these illustrations have been given for x centers, and as we just showed with the derivation of the translational dynamics equations, we would generally also need the y and z centers, so we have all the components of the position vector. For all of these illustrations, we begin by dividing up the object into a set of smaller segments of finite size. We then let the finite size become infinitesimal, and in so doing we transition from a summation over a finite set of objects to an integral over a domain. Within the integrals, the tilde quantity is the coordinate center of the differential element. For line segments, this exercise is a little tricky because we end up with integrals over a line segment or space curve that may have a complicated trajectory through physical space. We are far more comfortable performing integrals over a single Cartesian domain. For this reason, we begin by noting that we could use the Pythagorean theorem to write an increment of arc length dl as the square root of dx squared plus dy squared. Multiplying and dividing this result by either dx or dy enables us to write dl as one of these two expressions. As it is presumed that we know the function describing the space curve, we can evaluate the quantity inside the square root in terms of x or y as appropriate, and then have an expression for dl that can be evaluated by integrating over x or y. For area segments, we have these expressions where the tilde quantity again is the x and y center of the differential element. And for volume segments, we have these expressions where again the tilde quantity is the x, y, and z center of the differential volume element. For those of you who have not taken multidimensional calculus, the idea of integrating over an area or a volume may seem a bit intimidating. Not to worry. Everything we do will be reducible to a one-dimensional integral in x, y, or z, just like we did with the differential element of the line integral. This is generally not possible for an arbitrarily shaped volume similar to the one that's shown in this figure, but all the volumes we evaluate in statics will have one or more symmetry planes that will make reduction to a one-dimensional integral possible. In fact, we may run across symmetric areas in addition to symmetric volumes. When we do, note that we can state some of the components of the centroid directly without having to perform any calculations. The area shown here is symmetric about the y-axis. For a coordinate system positioned along this axis, the x component of the centroid is 0, and all we need to compute is the y component. For the hemisphere, there are two planes of symmetry for a coordinate system positioned at the center of its circular base. Again, there is no need to calculate y and z components of the centroid because they are identically 0. Only the x component needs to be calculated in this illustration. We will have two general approaches for calculating centroids. The first is the method of composite shapes. This approach works when the shape can be thought of as an assembly of relatively simple shapes whose centroids have been tabulated. If you have a physical textbook, you can find a table of centroids for some common line segments, areas, and volumes in the inside back cover. If you have access to the ebook, this information is probably available in a table or appendix. I am frequently asked if I expect you to memorize these tabulated quantities. Absolutely not. The only non-symmetric shape you should commit to memory is the triangle centroid. In the case of a triangle, the centroid is 1/3 of the height from its base, or 2/3 of the height from its apex. The reason for committing this particular result to memory is that we can consider many distributed loads as a superposition of uniform load, which it will turn out will look like a rectangular shape, and a linearly increasing load, which looks like a triangular shape. It is present routinely enough that you should have it mentally available, much like you should know the gravitational acceleration little g in SI and English units. The other approach we will use for calculating centroids is integration. This is possible for a wider variety of shapes whose boundaries can be described by known functions. In all of the problems we examine, differential area and volume elements will be reducible to one-dimensional integrals. In the case of an area element, we will use a rectangular strip that can be oriented either vertically or horizontally and will have its height or width described by functional boundaries with corresponding differential width in x or y. In the case of a volume element, we will restrict our calculations to symmetric bodies that can be modeled as a set of disk or cylindrical shell elements of differential thickness. I am always asked by some number of students who are taking or who have taken third semester calculus if it is okay to evaluate these area and volume integrals with multidimensional calculus. Knock yourself out. But a 2- or 3-dimensional integral in this class will not be necessary for any problem or example we do. In this first example, we are to determine the x and y positions of the centroid of the cross-section shown. This is a composite of two rectangular sections and a semicircular section. The centers of the rectangular sections are obvious, but what about the semicircular section? This is one instance of a standard cross-section whose tabulated properties are available. If we go to the inside back cover of the textbook, for instance, we find this figure showing us the coordinates of a centroid measured from the coordinate axes centered at the origin of the semicircle. The distance from the origin to the centroid in this case is given as 4r over 3 pi. Let's now go back to our example and find the centroid of the composite. In the first solution, I'll define the rectangular boundaries this way, and I'll call these 1 and 2. And we can see that their centers are right in the middle of these rectangles. I'll call the semicircular section 3, and we know from our table that its center is here, and that this distance is 4r over 3 pi. For the coordinate system we have defined in this problem with the origin at the upper left-hand corner of the section, the distance x1 to the center of the rectangle is just half its width, or 10 millimeters. y1 is half its height, but negative, so that's going to be minus 40 millimeters. And the area is just 20 by 80 millimeters, or 1600 millimeters squared. For the second rectangle, it has a width of 110 minus 20, or 90 millimeters, and so half that width will be 45, but we've got to cross 20 millimeters of the first rectangle first, So x2 is 20 plus 45, or 65 millimeters. y2 is minus half the height, which is minus 10 millimeters. And this area is 90 times 20 millimeters squared, or 1800 millimeters squared. For the semicircle, we have to cross the width of both of these rectangles, so we've got to go over 110 millimeters before we add on the 4r over 3 pi. So its x coordinate is 110 millimeters plus 4 times its radius, 40 millimeters, over 3 pi. And that number turns out to be 127 millimeters. Its y value is just the center of the semicircle, which is minus 40 millimeters from the origin. And its area is just half that of a full circle. And for r equals 40 millimeters, this turns out to be equal to 2513 millimeters squared. So now the center of the whole section is just the area weighted average of these individual components. So I could write it as A1 x1 plus A2 x2 plus A3 x3 over the sum of the areas. And if we plug in those numbers, we have 1600 millimeters squared. I'll leave off the units. All of these areas are going to be in millimeters squared, and all of the distances are going to be in millimeters. We'll end up with a result that's just in millimeters. But to keep this a little more compact, I'll leave off all those millimeter notations. So we have 1600 times 10 plus 1800 times 65 plus 2513 times 127 divided by the sum of those areas. And we calculate all that out, we get a value of 76.5 millimeters. Now we could do something similar for y. It looks exactly like the expression for x bar, but we have the coordinates of y1, y2, and y3 instead of x1, x2, and x3 in this area weighted average. And so if we take those areas in the y coordinates and plug those values in, we get minus 30.9 millimeters for y bar. For our second solution, I'm going to take the rectangular sections 1 and 2 as this large outer boundary here less this smaller rectangle here. So I'm actually going to be subtracting one rectangle from the other. The center of the larger rectangle is about here, and the center of the smaller rectangle is here. And the difference now is that we're going to have a negative weighting for the rectangular section that's actually absent. So here the center of the first rectangle is half of 110 millimeters, it's 55 millimeters. And y1 is minus 40 millimeters. The area is 110 by 80 millimeters, and that's 8,800 millimeters squared. The second rectangle is 90 millimeters by 60 millimeters. Its x center is, we have to go 20 millimeters across and then half of that 90. So again, x2 will be 65 millimeters. y2 we have to go down 20 millimeters before we go down half of 60, which is 30. So this ends up being minus 50 millimeters. And A2 is 90 by 60, or 5,400 millimeters squared. And we'll just note here that we're going to have a negative weighting for this area. So I'll write it as a positive quantity here, but because we're subtracting it from the cross-section, it will end up having a negative weighting. And we've already got the properties of the semicircle, so I'll just reproduce those And now, for instance, if we're calculating the average x position, this area-weighted average would look like 8,800 millimeters squared times 55 millimeters. And then the area 2, because it's a subtraction, it's a negative weighting, so it's now minus 5,400 times 65. And then we have plus 2513 for the semicircle times 127. And the sum of the areas, we have 8,800, and now again minus 5,400 for its negative weighting, plus 2513. And once again, if we calculate all that out, we get a value for the average x position of 76.5 millimeters. So as with many other of our problems, there are multiple ways of using a particular approach, the method of composite areas in this case, to get the same result. As a second example, we're asked to determine the centroidal x and y coordinates of an area bound by a line from above and a parabola from below. This problem is probably more easily solved using the integral approach. We will represent the differential area dA as either a vertical or horizontal rectangular strip, so we can make this a one-dimensional integral. If we choose a vertically oriented strip, the differential element has a finite height, differential width dx, and our integral will be in x. The height is just the difference between the top and bottom bounding curves, so our differential element dA can be written as the difference between the top and bottom boundaries times dx. The tilde coordinates in our integral expressions represent the center of the differential element, which is now right here. Since every material point within the strip has the same x coordinate, x tilde is just x. Just as with a rectangle of finite height, y tilde is in the middle of the rectangle, and this is a simple average of the top and bottom boundaries. From here, it's just a matter of substituting the expressions in x into the integrals and evaluating them. All of these expressions are polynomials, so they are easily integrable. The numerator and denominator of x bar are both quite straightforward, and they have these results. For the numerator, if we evaluated this integral, we could show that this is 1/3 x cubed minus 1/20 x to the 4th evaluated between these limits. And for the denominator, this ends up being 1/2 x squared minus 1/15 x cubed evaluated between these limits. The numerator of y bar is a little more work, as we need to multiply through the two terms in parentheses and evaluate the individual terms. Doing so produces 1/2 times the quantity x squared plus 1/5 x cubed minus 1/125 x to the 5th between these limits. And the results give us that x bar and y bar are 2.5 and 3 inches respectively. If we choose a horizontally oriented strip, the differential element has finite width, differential height dy, and our integral will be in y. Since we are integrating in y, we have to rewrite our bounding curves so that we have left and right boundaries in x as functions of y. Then the width of our differential strip is the difference between the right and left boundaries. This also suggests that the choice of differential strip might be determined by how easy or difficult it is to invert the original top and bottom bounding curves in x to make them left and right bounding curves in y. Even if we can invert them, the more complicated functional forms may result in more work to evaluate the integrals. Now the x tilde of the strip is a simple average of the left and right-hand boundaries. The y tilde is just y, since every material point within the strip has the same y coordinate. Substituting these expressions for dA, x tilde, and y tilde into the integral definitions produces these expressions. These are more complicated than those for the first solution, So we'll take a few minutes to talk about the calculation of the integrals. For the integral of x tilde dA, we might first note that we could write this as the x tilde 1/2 the simple average of the right and left boundaries times dA, which is the width, times dy. And this product will allow us to eliminate the cross terms. We'll end up with just the right boundary squared minus the left boundary squared. So we end up with, in this case, 1/2 of the integral of 5 times y minus 1 minus quantity y minus 1 squared dy between these limits of 1 and 6 inches. If we expand out this second term, this is y squared minus 2y plus 1. And so our integral is 1/2 5y minus 5 minus y squared plus 2y minus 1. And we can write that as the integral of minus y squared plus 7y minus 6. And the result is minus 1/3 y cubed plus 7/2 y squared minus 6y between these limits. If we plug the numbers in, this can be written as 1/2 minus 215 over 3 plus 7/2 times 35. If we plug these numbers in, we get this result, which is also 10.42 inches cubed. The integral dA is the integral from 1 to 6 root 5 times y minus 1 minus y plus 1 dA. For the first integral, we can pull out the root 5, and then just focusing on the square root of y minus 1 in the integrand, that integrates to 2/3 y minus 1 to the 3/2. And then the other two terms give us a minus 1/2 y squared plus y between these limits gives us this result, which is also 4.167 inches squared. Finally, we have the numerator in y bar. This is the most complicated of the three in terms of integration. Ends up looking like this. And here, if we focus on this first term, we can do this by substitution. If we let u equal y minus 1, du is dy, and the first term can be written as the integral from 0 to 5, 1 plus u times root 5u, which we can end up writing as root 5 times 2/3 u to the 3/2 plus 2/5 u to the 5/2 between these limits of 0 and 5. The second two terms integrate pretty easily to minus 1/3 y cubed plus 1/2 y squared between these limits of 1 and 6. And so putting all these numbers together, we end up with 2/3 of 25 plus 2/5 of 125 for the first term. And then we end up with minus 1/3 times 215 plus 1/2 times 35 for the second terms. And that also gives us 12.5 inches cubed. So we get exactly the same results for the horizontal strip that we had for the vertical strip. I will try to avoid problems, especially on exams, that require you to demonstrate your mastery of various substitution and manipulation techniques to evaluate integrals. I expect you to be able to evaluate integrals with integrands consisting of simple polynomials and trig functions. Anything beyond that is not necessary to demonstrate your knowledge of how to calculate a centroid and amounts to just showing off. As we have already noted and is mentioned again here, sometimes the choice of one orientation over the other will make the integral much easier to evaluate. Other complications can also drive the choice. In this case, for instance, an x integral has to be broken into two different integrals as we have a discontinuous change in the bounding curve from the bottom. The integral in y can be performed in a single integration, so it is probably a better choice. In this third example, we have a truncated circular cone and wish to find the locations of its centroid. Note that the symmetry of the object tells us right away that the x and y components of the centroid are 0, so we only have to find the z component. This is a problem we can do using either the composite approach or the integral approach, so we'll use both. Using the composite approach, we can see that this truncated cone could be represented as the difference between a cone of height 12 inches and base radius 3 inches and a cone of height 8 inches and base radius 2 inches. A cone is one of the volumes with tabulated properties, and we can see that it has a volume of pi r squared h over 3, where r is its base radius and h is its height, and that its centroid is 1/4 of the height from its base. You might notice that the centroid is labeled G, something we normally associate with center of gravity. In the case of a volume of constant mass density, there will again be no difference between centroid, center of mass, and center of gravity. We treat the cone we're subtracting as a volume with negative weighting, and that enables us to evaluate the z component of the centroid as follows. So we'll call this volume 1, and we'll call this volume 2. Volume 2 will end up with a negative weighting. You can see that that's represented here. Volume 1 has a volume of pi over 3 base radius squared times height, which is pi over 3 times 3 inches squared times 12 inches, and that number turns out to be equal to 113.1 inches cubed. The z component of its centroid is 1/4 of its height, and with h equals 12 inches, this ends up being 3 inches. For the second volume, the base radius is 2 inches, the height is 8 inches, and that gives us 33.51 inches cubed. The z-coordinate of its centroid requires us first to go up to the bottom of its base, which is 4 inches, plus then h over 4, which is 8 over 4, or 2. So the z-coordinate for the second volume is 6 inches. The centroid for the object then is v1 z1 minus v2 z2 over v1 minus v2. That's going to be 113.1 inches cubed times 3 inches minus 33.51 inches cubed times 6 inches over this difference of 113.1 minus 33.51, and that result ends up being 1.74 inches. As an alternative, we can evaluate the centroid based on a differential volume element consisting of a disk of radius r, which is a function of height z. The disk has thickness dz. Every material point within the disk is at the same height z, so the z tilde will also just be equal to z. We first need to have an expression that describes the radius as a function of z, and we can see that at z equals 0, this is going to be the base radius of 3 inches, and then this tapers down to a radius of 0 over a height of 12 inches. So the functional dependence for this would look like 3 inches times quantity 1 minus z over 12 inches. Our volume increment is pi r squared, that's the area of the disk, times its thickness, and that ends up giving us 3 inches squared is 9, so we have 9 pi times the quantity 1 minus z over 12 squared dz. So now we have two integrals to evaluate. One is just the volume, is the integral of dv. We're integrating over z from 0 to 4 inches. So this looks like the integral from 0 to 4 of 9 pi 1 minus z over 12 squared dz. And we can show that that result is 9 pi times minus 4 quantity 1 minus z over 12 cubed, evaluated between these limits of 0 and 4. And that gives us a value for the volume that's 9 pi times 4 quantity 1 minus 2/3 cubed, inches cubed. And that turns out to again be 79.59 inches cubed, which you'll notice is exactly the difference between the 113.1 and the 33.5 one we did with the composite calculation. Finally, the last thing we need to calculate is the integral of z tilde dz that goes in the numerator of this centroidal calculation. That ends up looking like 9 pi times the integral from 0 to 4 z for z tilde times 1 minus z over 12 squared dz. And here we will benefit from expanding that square. This ends up looking like 9 pi integral of 0 to 4 z minus z squared over 6 plus z cubed over 144 dz. That gives us 9 pi times the quantity z squared over 2 minus z cubed over 18 plus z to the 4th over 576 between these limits. And that gives us these numbers, which gives us 138.2 inches to the 4th. And once again, our z centroid is the ratio of these two integrals, and that gives us, in this case again, 1.74 inches. So if we do the problems consistently, it shouldn't matter whether we use the composite approach or the integral approach. As with many of our other problems, we should choose whatever it seems easiest to us to allow us to get the answer most efficiently.